Oh, there we go. I can feel it. Yeah. I should probably just like start a Zoom call and put it on people's laptop screens. Would be close enough. Yeah, yeah. I think we're good. Right. Glance at my notes and make sure that I remember how to do this stuff. I'm trying an experiment. We're going to use this like fancy doodad. See if that works. Okay. Got 2 more minutes until class starts. This is great. Is there like a paper towel or something I could use? Honestly, this is fine. It's like some. Yeah, careful, it's an obstacle course. Oh no, wait, it's gone. It was so good. It is on. It was. I mean, it was displaying a minute ago, and I haven't touched it. We're so close. Hey. Yeah, so it's stage left. So that's just isn't doing it. Oh, because it's on the wrong. Because it's stage right floor box, which is this guy, right?
Oh, I see. But
So now stage left projector. There you go. Oh, don't, okay, we're good. Don't touch it. All right, guys. Well, by some miracle, we've managed to start on time. I'm glad that Leticia and I and Mark showed up a full 15 minutes early here, because apparently that is what it takes to turn on a projector. Nice to see that half of you survived the weekend. We'll see what I can do to scare out the other half by the end of this week. Right, so welcome to lecture 2 of whatever course number this is, 67350. I have never taught the same course number consecutive, like, at all in the last, like, 4 years. So today, we're going to continue our discussion of numerical methods and start to dive into actual algorithms instead of the really boring low-level stuff. Before we get started, a few announcements, reminders, all that good stuff. How many of us have like found the homework on Canvas/Gradescope? Fabulous. How many of us have finished the homework? There's usually one. No? Okay, too bad. Great, so as a reminder, the homework is intended for like a full 2 weeks effort. This is a grad level course, it's a TQE. So like read the problems now. By the end of today's lecture, you've got more than enough background to do, I think probably most of the assignment. So give it a shot. There's office hours. I think Leticia, you have office hours after class today, right? Excellent. And then Mark, I believe, is tomorrow, and or no, I'm tomorrow. I'm tomorrow. And he's tomorrow. There's so many office hours. And then there's more on Wednesday. So like, you know, make ample use of everybody's help. We're here for you, and really it makes it much easier when you have your course staff do your homework. I mean, help you with your assignments. Beyond that, a reminder that this class, starting this Friday, will have these sort of regular quizzes. These are like they're intended to take like roughly the length of like a Wordle. Like they're not supposed to be that hard. We'll give you a 48-hour window to take it. I think we converged on like Thursday and Friday. Is that right? So that'll go up probably like sometime in the 24 hours after class on Wednesday. We'll send you lots of reminders because inevitably you guys are going to somehow forget to do this. But it's really just to hold you responsible for the contents of lecture. So just like, you know, page through the slides a little bit, review, and hopefully you'll be all right. That's it for announcements for me. Any questions, comments, concerns from the peanut gallery here? Fabulous. Well, today we are going to continue our discussion of error and numerical methods, and then hopefully we're going to get to linear algebra, everybody's favorite topic in this field. So where we left off in our previous lecture, we spent some time talking about the IEEE 754 floating point format and other ways to, you know, specify a floating point number. Remember that there's some number of bits that are dedicated to the true value, some number of bits that are dedicated to the exponent, and then probably one to the sign. And that's sort of the standard for a lot of floating point calculation. By the way, one of the students after class on Wednesday sent me a pointer to like these super cool new systems that are reconsidering all of these floating point constructions in the world of AI. There is one pointer in the course notes, and in fact, apparently in the last year, there's even more thinking about this stuff. Like, for example, maybe using this sort of the same floating point format per block of like a tensor, the kind of thing that happens in PyTorch, and then kind of shifting it once per matrix as opposed to once per value. Oh, there are all kinds of clever tricks people use to shave off calculation so that you can do high-speed training for machine learning. But in any event, the main takeaway from the previous lecture is that in this class we got to fudge stuff, right? Like the calculations that we're going to do are rarely going to be exact. Everything is approximate. They're rounded, they're bracketed, all that good stuff. A lot of the algorithms that we're going to write down will only iteratively converge to the solution. We're not going to be able to actually just say, after 15 steps, even in the presence of perfect arithmetic, we solved our problem. Actually, the one exception to that will be Gaussian elimination, which we'll do hopefully today. And so because of that, it's really worthwhile to begin any discussion of numerical methods by thinking about all the different sources of error, how to quantify it, and how to make sure that we're like okay with the error that we've measured in an algorithm. And in particular, a theme of today's lecture is going to be the fact that there's error you can measure, and then there's error that you care about, and those two things are typically not the same. Right? So just to get you thinking about that, I think everybody's definition of error is roughly like the distance between your solution and the true solution to your numerical problem. Is that something that I typically have access to during my algorithm? Like, obviously not, right? Because if I did, then I would just use that, right? And so we have to bound error in different ways or use proxies for error that we hope are okay and are going to depend on a notion that we'll call conditioning. So that's our high-level story. So as a bit of a reminder of our end of our previous lecture, essentially what I wanted to do was enumerate all kinds of different places where error shows up in numerical computation. So we spent most of our previous lecture talking about error that shows up in floating point computation, but that's not the only thing. For example, there's discretization error, like using this divided difference on the right-hand side of the expression as some kind of proxy for the derivative of f of t. There's modeling error, like neglecting small perturbative noise or having the wrong, using f equals ma for physics when we all know that we should be doing all our physical simulations using, I don't know, what's the grand unified model of whatever. And even input error, like a lot of our calculations and numerical methods are built on sensor input or data we collect from the wild, which actually probably has way more error than, for example, the floating point calculations that we're doing, which should give you some perspective in these algorithms, right? Like, does it make sense for me to run an algorithm to like 50 digits of precision if the data coming in is only 2 digits precise to begin with? Well, probably not, right? So these are the kinds of things that we think about in numerical methods that distinguish this field a bit from classical algorithms and some of the things you might have seen in undergrad computer science. So just to kind of get our minds thinking about this stuff and to wake up, it's 11 a.m., so I know our grad students have just gotten out of bed. Let's think for a bit. So what are the kinds of sources of error that we might see in simulating the stock market, like a financial simulation? This is an easy one. Come on, these are like messy. Yeah. Interesting. Yeah, that's absolutely right. So like a lot of times you do financial calculations and in some sense pretty low number of digit regime. So there's some rounding, right? What's that famous movie from the 80s where they like round down all the ATM transactions and make a profit by that little margin? Ah, you kids. Any other sources of error? That's it? Other than that, like if we just use perfect numbers, our finance, we could predict the stock market? Yes, Alice. Modeling error. That's right. So for example, I think the most famous equation in finance is probably this Black-Scholes equation. From my perspective, you would just call this diffusion. It turns out it took me about 20 years of a math career to figure that one out. These are models, right? I mean, they're models of really complicated human behavior. And chances are there's no partial differential equation that's going to predict the stock market. Because if there were, we'd all, well, I was going to say we'd all be rich, but chances are we'd just have a different system, I think. Anything else? Yes. Input error. Yeah, that's absolutely right. That's absolutely right. So like in order to predict the stock market, for example, you need to know all the market conditions as they change. By the way, even, I mean, never mind the outside conditions. One thing that I learned, so my partner works at one of these like financial data companies that serves up this kind of stuff. And one thing that I learned from him is that even just getting data, like the state of the stock market, for example, is not so easy to do. I mean, by the time you read that information, it's probably changed. Yeah, anything else? Yeah. Absolutely, latency, all of these things are good sources of error. Notice that, like, essentially, I mean, it's not a thing that we like to think about as computer scientists, but absolutely, all of these things should help us determine algorithmic efficiency, right? Because at the end of the day, again, if we run, you know, we have our favorite financial model, like, there's no reason to run it at super high fidelity if the stuff going into our finance simulation is super gross, right? And so these are the kinds of considerations that matter in this kind of discipline. Okay, so hopefully we all admit, agree, have come to acceptance that there are likely errors in the calculations we'll do in this class. By the way, when I say error, I mean like numerical error. You guys, of course, will do perfect non-error on your exam. And so there's a lot of different ways that we can quantify error. And the kind of thing, you know, these definitions start out easy, and then as you go through problems in this course, you should go back to these definitions and see if you really can map them on, because I think it gets harder and harder as we progress. And that's because, unfortunately for us, actually measuring error requires access to the solution to our problem, which we typically don't have, right? There are things that we can do. For example, a typical thing that happens in a lot of academic papers is you like prove a theorem saying your algorithm converges if you run it long enough. So then you run it for like 10 years, and then you like compare that to what it looks like after 3 days, and that's like some proxy for error. But notice even there that like that's still not exactly right? You still don't know if, like, for example, in 10 years plus 1 day, suddenly your algorithm takes some giant step toward the right answer. Probably not, but you never know. So and when we talk about error, there's a lot of different ways that we can measure it. And in this class, what we're going to see is that we're typically going to want to bound it or use a proxy. Yeah? So the type of error that we typically care about, there's sort of two different ones, depending on the context. One is absolute error, which is just the distance between the solution of your problem and the thing that you got. And related to that is relative error, where you just divide that by the true value, probably with an absolute value around the outside, right? So of course, the first one, the units will be in whatever the units of your numerical problem is, you know, inches, feet, whatever, centimeters for our European colleagues. And the relative error is in percent. And depending on the application, one of these might matter more than the other. In fact, I think I see a lot of computer scientists and people in machine learning use absolute error in totally shameful ways, like, you know, oh yeah, my stochastic gradient descent converged to like 3 digits, which of course is like meaningless, right? If I took my data set and I just scaled all the data points by 10, my machine learning problem probably wouldn't change, but like suddenly that 3 digits is less useful, right? Right, so like to give you the kind of, you know, high school version of this picture, you know, here we have two different ways to talk about error, you know, like 2 inches plus or minus 0.02 inches as opposed to plus or minus 1%. And I think we can all agree that one of these is absolute and the other is relative. I'll let you guess which one is which. Okay. So in numerical methods, things become a little bit subtle when it comes to even measuring these things. So let me show you kind of a wild plot. I think this is actually, you play with exactly this plot on your homework. It took me a long time to convince MATLAB to actually generate this figure. It like really doesn't want you to do shameful numerical stuff, which is good. So believe it or not, this plot here is a plot of the function e to the x minus 1 over x, all that minus 1. Yeah? Which you might not, you might feel is nice and differentiable, but at least according to MATLAB is a pretty wild function close to 0. So what's going on here? Any ideas? Well, if you look at the scale of this plot, notice that the x-axis goes to like really tiny numbers, like 10 to the minus 8. Yeah? And so what's happening here is you're in the regime where suddenly numerical stuff starts to matter a lot, right? You're in the regime where you're in the last couple bits of this IEEE floating point. And in particular, notice that things like exponentiating can really easily start changing what order of magnitude you're in. Okay, so this is a fantastic example of a phenomenon in numerical methods called catastrophic cancellation, which I love. It's like a super extra term for like a pretty simple phenomenon, which is essentially saying the following. Anybody brave enough to tell me the Taylor series for e to the x? 1 plus x. Maybe give me one more. Plus x squared over 2 plus x cubed over 6. Plus, okay, fine, we'll stop. But in particular, e to the x is roughly 1 plus x. So e to the x minus 1 is roughly x, right? But here's the problem. What is x for small x? Well, it goes to 0, right? And so the difference between these two values gets smaller and smaller and smaller, right? And so this is the kind of thing that can happen in numerical methods. Remember, we talked in our last lecture about kind of traversing different orders of magnitude, right? So e to the x kind of looks like the number 1, so it's like in a pretty reasonable regime. Once we subtract 1, suddenly we're subtracting two numbers and ending up with a really small thing, and that's what's kind of noisy, because essentially, in some sense, we're looking at stuff that would probably be considered error relative to the value of e to the x, right? So this is a good example where like absolute error rather, and relative error are very different, right? Now notice that like the absolute error here is kind of bounded above, like roughly by 10 to the minus 7, right? But what happens to the relative error? Yes? That's exactly right, right? I mean, so this quantity, in fact, I've even given you the limit here, right, is 0. So basically, I'm dividing some number that's between, you know, plus or minus 10 to the minus 7 by something that gets smaller, 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 right? And as I divide by numbers close to 0, the error kind of blows up as a percent, right? So there's no right or wrong answer. Like, what notion of error should I have used for this calculation? For some places, relative might matter. For others, absolute. This is a good example where they're very different. Yes?
I want to clarify. So e to the x has the Taylor series of the first two terms is 1 plus x.
That's right.
You're saying the 1 minus 1 is what's causing the catastrophic cancellation?
Yeah. So basically, like, think about the relative error. So by the way, there's a lot of numerical error that happens in this calculation. One of them is like your CPU does not have an e to the x chip, right? So it's approximating this value. Chances are, by the way, it does it to full digits of precision because exponent's kind of important. But the error in this expression, right, even if you have like an itty bitty amount of relative error, I mean, notice that it's like the relative error is relative to 1, right? Whereas so like if I get the last couple digits wrong, maybe my e to the x computation is kind of okay with that, right? But now when I subtract that 1, we've traversed regimes, and we basically just revealed all of the numerical error in the exponential. Yeah. Yes, on. Why are you getting the spikes in the plot? My best guess is like that's roughly where some part of this calculation, the what's it called? The exponent is changing in the IEEE. I don't know. It's a good question, actually. I should go back and see if those align with powers of 2. That would be my guess. Yeah. Yes?
I guess for catastrophic cancellation, is the idea that like because e to the x is close to 1, we're forced to have like the 1.
That's right. The 1 is the significant digit. So suddenly, all of the significant digits for e to the x minus 1 are relatively limit, right? Because they're like far away.
These have like 50 zeros and maybe like 2, 3 digits after.
That's right. Whereas if the 1 weren't there, I could shift that whole value over. Yeah. Okay. So, right. So here's the basic issue with measuring most notions of error is that you really can't compute it for the reason that I said, right? Like computing error requires actually knowing the solution to your problem. And of course, we don't know that because that's the whole point of these algorithms. And so typically, our solution here is to be conservative, right? To bound it or to use some proxy that we think is related to error in some way that's pretty reliable. Does that make sense? Okay. So let's talk about what that means. So let's say that I study the root finding problem. So I'm given access to some function f. By the way, hopefully you guys are familiar with notation. In case you're not, f is a function that inputs a real number and outputs a real number, right? So it's a function, one variable. Gosh, this board is so high. Ugh. Right, so maybe here's f. Okay, so what is a root finding algorithm trying to do? It's trying to find a location where f of x is equal to 0, right? So maybe my algorithm gets a little wrong, and it guesses like my root is somewhere here. Yep. And so typically, by the way, in numerical methods, we'll use a little star to denote the true solution to our problem. And then I think in our textbook, I often use the sort of XEST for like estimated solution to our problem. Does that make sense? Okay. Can anybody name some algorithms for root finding, by the way? We'll cover this later in this course, just out of curiosity. Yes? Newton's method is the most famous one. Any others? In 1D? Secant method, that's another. Yes. Robbins Monroe. Oh, look at you, hipster. Yes. What was that? Bisection. Yeah, that's probably the easiest one, right? You find a point where it's positive, a point where it's negative, and you do kind of binary search to find the root. These are all different algorithms, and we'll see that they all have different convergence rates and different guarantees, right? So for example, Newton's method requires a derivative and a pretty good initial guess. Bisection unconditionally converges for continuous functions, but you need to be able to at least bracket a root. Great, so there are lots of algorithms out there, and now we'd like to measure some notion of error. So the reality is I run my code for Robbins Monroe or whatever my favorite algorithm is, and what I get is a point x est, and sadly for me, that it's not a perfect root. So probably what happens when I put it into this function f of x is I don't get exactly 0. I get some number whose absolute value is way less than 1. Does that make sense? Okay, so what is, oh no, now I see the bug with using this tablet for lecture, which is that it falls asleep. Okay, well, that's fine. So what is the error here of root finding? We'll say absolute error. For now, well, I think we can all agree that it's just the distance between x est and x star, right? And of course, we can't compute that. I'm just going to keep repeating this, because if I did know this, I would take this difference and add it to x est, or subtract, I guess, and have a better root. That wouldn't be so good. What can I do? How can I guess whether I'm like pretty close to a root? Well, remember, yeah, on. Yeah, I can use the value of f as a proxy, right? Remember that I'm trying to find a point where f of x is equal to 0, right? So what could I do? I could take x est. I have access to the function f, right? So I could just evaluate it. If I get like 10,000, I get bad vibes from that, right? I probably want like 10 to the minus 5, yeah? So in other words, there's actually sort of two notions of error. We're going to give them a name. So we're going to call this forward error. I'm going to be lazy and write FW. Okay? Can you guess what the other error is called? Backward error. Thank you. I think you guys are starting to figure out that this lecture is a lot less painful if you just answer. Okay, so in particular, in this case, it's probably just f of x est. Okay? And these are two different notions of error. And notice that like they're correlated, but they're not exactly the same. And in fact, it's really hard. I mean, what we'd really like is for backward error to be predictive of forward error, right? Because this is the one we can measure. And notice that that's kind of true and kind of not. In particular, let me give you two different examples. Here's one function, and here's another. Oops, I didn't make this difference clear enough. In fact, let me revise the picture on the left. Let's see. Hopefully you'll get what I'm trying to do. It's really hard to do this in front of you guys. Right, so here's x star, here's x star. Like that, okay? Okay, so what's the difference between these two things? Well, if I look at the slope of f near my root, right, one of them is kind of sideways and the other is pretty vertical. And now let's think about what that means in some neighborhood of x star. Right? So I run my numerical algorithm, I get some point like that, and I measure the value of f. So in other words, I kind of look at the vertical axis in this plot, like that, as opposed to, let's see, this is roughly the same distance. What's the difference between these two pictures? Notice that like up to my bad drawing, the amount of absolute error is pretty close between these two things. But here, the backward error is pretty small, right? Let's suppose over here, the backward error is pretty large. And the difference between these two things is the slope of f through our point x star, right? I see your hand. I'll get you to it in just a second. So essentially, notice that in the picture, this is what's a little counterintuitive. In the picture on the right, backward error is a good proxy. Because again, if I have small backward error, then I have small forward error, which is the error I care about, right? Whereas over here, I have a relatively small amount of backward error, right? Like I have a point where f is close to 0, and yet my x and my x star are far off from one another. This is backward. It's counterintuitive. I always get it the other way around. Okay, yes, your question. So the question was, why don't we try to normalize a backward error? We could. For example, I think you're suggesting basically to divide it by f prime. Here's my question: where do you evaluate f prime? You probably want to evaluate it at x star, but sadly we don't know where that is. If your function were Lipschitz, you might be able to do such a thing. Yeah, great question though. Yeah.
What do you mean when you say like one of them is like a good proxy and one of the graphs is not a good proxy?
So yeah, so to repeat, essentially, remember that backward error is the thing that we can measure, and what we want to be able to say is that, oh, my backward error is low, and hence my algorithm was successful, right? Here I can say that, right? Because essentially, if my backward error is low, well, that means I'm in a pretty small neighborhood of my root, right? Over here, if my backward error is low, I'm actually in a pretty big neighborhood of my root. Yeah. Fabulous questions. Okay, so hopefully we're starting to get the picture and why this is a little bit subtle. Let's see if we can do a second example here. Let's say that I wrote a piece of code for computing square roots. It's another typical one, right? And let's say that I make the approximation that the square root of 2 is roughly 1.4. Roughly right. Okay, so then what is my forward error probably going to be? Well, I would say it's 1.4 minus the square root of 2. If you're curious, this is 0.0142 ... right? What would the backward error be? Probably in this case. Like, what's something I could measure? Yeah, I could square everything, right? So I could say 1.4 squared minus 2. Notice that this is actually a calculation I can do with exact precision, right? Whereas the previous one I really can't. You know? If you're curious, this is 0.04, not that that's a particularly meaningful number. Okay, so hopefully we're getting the idea here. Okay? Right, so essentially, this is one of these things where I think the vibe of the definition of forward error versus backward error is pretty clear. Like, one is measurable and one is not. It's actually really hard to kind of pin down a precise definition of these notions. In this class, because I struggle with this, like on exams and stuff, I'll make it pretty clear what I mean. I think a very typical definition, which is the one we go with in the book, is that forward error is just the error in the solution. That one's not so hard. And backward error is the amount that the problem statement would have to change in order to make the problem solution exact. This feels a little bit weird, but let's see if we can wrap our heads around that. So for example, in root finding, what is the problem statement? Well, one could argue that the problem statement is like, you know, find an x so that f of x equal to 0, yeah? But there's like a bigger class of problems, which is find an x where f of x equals to c, right? And notice that if c happens to be equal to the value of f at the point I just found, then I solved it perfectly, right? So in some sense, this absolute value here, this backward error, is saying, well, if I move around the right-hand side of my root finding problem to just match the value I got, right? That's some notion of error. Does that make sense? This is abstract and like weirdly hard to think about. I wouldn't worry about it a whole lot. I think like can measure versus can't is also perfectly sensible. Yes? Is there a sense of relative error for backward error? Yeah, possibly. I think it's sort of problem dependent. Like in this case, probably not, because you'd be like kind of dividing by 0. Yeah. Unfortunately, a lot of the answers I'll give you today are like, yeah, it's problem dependent. This is all, you know, you do what you can. Other questions that I can waffle on? Fabulous. Okay. So I guess we just did the square root example. Another one is for linear systems of equations. So in case you haven't got the drift yet, like we're going to spend a lot of time talking about algorithms for, you know, given a and b, find x, right? So, right. So what would be the forward error in this case? Hopefully you guys are getting the point that like this would be roughly x estimated minus x star, where in this case x star is equal to a inverse times b, assuming that such a thing exists. By the way, in this case, I guess it should be distance. I think the standard is to use L2 norm, but this is one of many things that you could change in your notion of error. That makes sense? So there are a lot of different notions of backward error, and it kind of depends, like when we say problem statement, what do we mean? Like in this case, notice that your input is A and B, right? So you could imagine that there's actually multiple definitions one could use. I think in this case, the easier one is to think about just changing the b, right? So in particular, let's think again about error I can measure, right? So let's say that I have an algorithm for solving linear system of equation. If I shut up, we'll manage to get to one later today. So what do? They input a and b and they output x. So I could take the x that I got, multiply it by a, and see how close that is to b, right? That I can do. So in other words, I could have a times x estimated minus a times x star, and this is just b, right? So this is actually a value that I can compute. Does that make sense? Okay, so we're going to add 2 more vocabulary words. I promise this is going to get more interesting soon. I'm sorry, the beginning of a numerical methods course is always kind of boring. And that's essentially, we want to be able to evaluate, like, when is a problem a numerical problem that I expect to be able to solve well, and when do I think it's going to be really hard? And essentially, the terms that we typically use for that are well-conditioned and poorly conditioned, or because a lot of numerical methods have their history in the UK, it seems that often we call it ill-conditioned. Yep. So if we go back to our root finding problem here, which of these 2 problems is well-conditioned? Probably the one on the right, right? Yeah. Notice that you can't just say, like, and probably the one on the left, because, like, essentially backward error is a bad proxy here. We're going to say is ill-conditioned, right? Sometimes, by the way, another phrase people use, especially in differential equations, is numerically stiff. That's a phrase you might have heard. If you look at Leticia's most recent research paper, that's what she would use, because it comes from the universe of, like, vibrating materials. And as materials get really stiff, what we're going to see when we talk about differential equations, they become harder and harder to simulate. Yeah? This is a big problem for, like, protein simulation, because proteins have, like, some forces between atoms that are really gigantic and, like, lead to very high frequency vibration, and then other forces that are, like, little slow schloopy vibes, and then, like, they all have to get resolved together into one thing, which happens at very different time scales. Okay, so, right, and we've seen a good example here. Yes? Stiff would be ill-conditioned. Yeah. Weirdly, I don't think people say a problem is loose if it's well-conditioned, but I suppose you could. Other question? Cool. This is all basically to just give us, like, some baseline language. And so the final thing that we should ask is, how do you actually measure how well or poorly conditioned a problem is? And a very typical measurement, which kind of makes sense given what we set up so far, is something called the condition number. Okay? And the condition number is a ratio of forward to backward error for a given problem. Typically, when we talk about condition number, we like, can we actually compute it? No, because again, we don't know the forward error. So what we're going to try and do is bound it for different problems, maybe at least, like, in some small neighborhood of the optimal solution, I think is a typical thing to do. And we'll see an example of that in a moment. By the way, do we want condition number to be big or small? Small, right? Because we want a small amount of backward error to imply, or sorry, a large amount of backward error to imply a small amount of forward error is kind of the better situation to be in. Yeah. Yes. Sure. Yeah. So condition number is ratio of forward to backward error. So let's say that I have a well-conditioned problem, right? What is that going to say? It's going to say that even if I have a large amount of backward error, the amount of forward error is very small, which is the situation you want to be in. Yeah. Typically, the condition number is bounded below by 1. Again, kind of depends on the problem, but we'll see that in a minute. Okay. So let's do an example. We're going to continue talking about root finding. In fact, somebody asked a question, I think you did earlier, that I think kind of guessed the right condition number for this problem. But let's actually see if we can do it, which is for root finding. So again, remember the point of a root finding algorithm is you're given access to a function f, and you're trying to find a point where f is equal to 0. And based on our picture, we can see that the slope of our function has something to do with that. And let's see if we can make that more formal. Okay? So By the way, in this case, we're going to talk about the conditioning of root finding for differentiable functions. Like an interesting challenge is to think about how you might go about this calculation if you don't have a derivative. Short answer is you can't. But in any event, let's see if we can do it. So, right, so remember that the condition number is equal to the ratio of forward error to backward error. Like that. By the way, on last year's homework, we had a really awful problem where I had these people, I had our students work out like condition number and all these different notions of error for like evaluating softmax in a machine learning system. And the feedback I got was like, oh my God, don't make me do that. So this year's homework, I think, is much easier for that particular problem. Okay, but in particular, let's say that I'm going to simplify our no, that's okay. Let's say that our root here is going to be x star. By the way, when I say root, that's like the true point where f is equal to 0, just so we're all on the same page. And in particular, let's say that the thing that I got is equal to x star plus some epsilon for some small shift. Obviously, if I have x, I can get epsilon and vice versa. Okay? You can probably guess where I'm going with this. All right. So there's our notation. So what is our forward error of our problem? Epsilon, right? Because remember that forward error is the difference between the true solution and the estimated one, which in fact I've kind of defined to be epsilon. Actually, you guys are slightly wrong. What's the true forward error? Like the absolute value of that, yeah? Okay, so got the absolute value of epsilon on the top. What's the backward error? Well, in some sense, it's f of x plus epsilon, x star, I guess, minus f of x star, which is just 0, like that. Cool? Okay, so in this class, usually when we talk about condition number of a problem, we do assume that our algorithm isn't like totally terrible, meaning that like it gets you within some ballpark of x star, right? And if you make that assumption, then essentially what you can kind of guess is at the very least like the Taylor series is probably a valid thing to use in this case. Does that make sense? So like typically, you don't need to measure condition number if you like ran your algorithm and it gives you an answer that's like completely unreasonable, right? I think that's the basic logic here. Okay, so in particular, right, so let's actually just substitute in the Taylor series for f. So we've got absolute value of epsilon in the numerator. So what is the Taylor series around x star? Well, what's the constant term? It's f of x star, which by definition is 0, yeah? So the second term we're going to get is f prime of x star. I'll move out of the way in a second. I'm sorry, I'm left-handed. Okay? And then the third term, we're going to just call fudge factor. Okay? So in particular, we will say that this is O of epsilon squared. Okay? By the way, in this class, a thing that you guys should review in the textbook is that big O does not mean what you are used to from algorithms class, because what we care about are small numbers, not big numbers. Okay? So this is kind of like plus a Taylor series term that looks like epsilon squared. Okay? And you can read in the textbook the formal definition of that. Okay. So notice I can take the top and the bottom and I can divide by epsilon here. Right? So this is 1 over f prime of x star plus big O of epsilon not squared, like that. Make sense? And so in some small neighborhood of our root, this is like roughly equal to 1 over absolute value of f prime of x star, which is sort of exactly what we would expect, right? Because remember that a big f prime is a well-conditioned problem, and this is inversely proportional to f prime. Does that make sense? Yeah. Yeah, so the question was, why use the Taylor series and not take a limit as epsilon goes to 0? You could do that. This is just a lazy proof. Yeah. Yeah, so what if f is not differentiable at x star? Great question. Then this methodology doesn't work. So you need some other way to bound the quantity that you started with. So a typical thing to do would be to put some bound. So for example, like a Lipschitz bound is a very typical one, which is sort of some rough notion of being upper bounded in slope. Yeah. But yeah, you're right. This methodology wouldn't work. Yeah.
Wait, but how do we know f prime of x star if
We don't. Great question. Oh my gosh, you hit the nail on the head. Here's a really irritating philosophical thing. We derived a formula for condition number. This is a perfectly fine formula. But our colleague asked exactly the right question, which is, how do I actually compute the condition number? You notice this is kind of a problem because, like, there's an x star in there. So there's actually a couple different methodologies that people use. One is to look at the form of f and assume that the slope is bounded everywhere, if you're lucky. Sadly for us, a lot of f's don't have that. A different thing that we might do, which feels a little shameful, but it's the best we can do, what do you think, is probably plug in the estimated x here, which of course, as you can probably think of, there are cases where that's not such a good proxy, right? In fact, if you really want to like mess up your brain and get philosophically like totally confused, you could ask a completely reasonable numerical analysis question, which is, what is the condition number of estimating condition numbers? Yeah, or like, what is the condition number of estimating a condition number estimate? Right? You can do this, like it's turtles all the way down. Like these are hard problems. So I think this is kind of where theory meets practice. Like if you run a piece of numerical software, probably what it'll do is estimate the root and then report the value here, like at the estimated root. But of course, as you say, there are cases where that might not be so great. Yeah? But on the other hand, I think one thing that this formula does give you is some notion of like just pictorially what are well-conditioned and ill-conditioned problems for root finding. Let's take this to an extreme. What's an example of a super ill-conditioned root finding problem? Well, probably one where f prime is equal to 0, right? What does that picture look like? Well, now you're at the root, your slope like is parallel to the horizontal axis. So from like a microscope perspective, like it's pretty much impossible to distinguish the root from other stuff nearby. Like it vanishes really, really fast. Yes?
Is the expression f prime of x star epsilon plus epsilon squared just the generic Taylor series expansion of f prime of x star plus epsilon?
Yep, this is just generic Taylor series about x star. Remember, there's no first term because we're doing root finding. Yeah. Other questions? I'm good. This is great. You guys are awake. It's early. I love it. This is fabulous. Okay, so in any event, hopefully we now understand that like these are hard problems. They're subtle. Even estimating how hard a problem is itself a subtle problem. In this class, we're going to return to this theme many times. We'll talk about many different numerical problems. And as we do it, the very first question we ask before we even talk about algorithms is going to be whether we can solve that problem at all and how reliable we think our algorithm can be, which, as we can see, may have nothing to do with the algorithm itself. Yeah? Okay. So on the practical side, so that's the theoretical picture. I think on the practical side, one thing that we're going to learn is that small adjustments to the calculations that you make can make big differences in the quality of the actual output of your numerical code. Right? We already saw that in this one example with this crazy wiggly function with just e to the x minus 1. But there are many examples of that. So here's a nice one. Let's say that I wanted to estimate the norm of a vector. Right? So remember what is the norm of a vector? Well, it's the square root of the sum of the squares. So I could write a perfectly reasonable looking piece of numerical code in my outdated C++ because I'm old. Yeah? What could go wrong here? Any ideas? Yeah. That's exactly right. So like if x has pretty big elements, right? Then those elements, when I square them, are going to be really, really big. Yeah? And in fact, I think we're going to skip it because we're a little low on time. The textbook even proves a little bound, which I feel like is a pretty reasonable one, which is as follows. Essentially, if I look at my vector x and I look at all of its elements, then one thing that you can show is that the minimum over all elements of the absolute value of xi is less than or equal to the norm of x divided by the square root of its dimension is less than or equal to the max. And I think the way to think about this bound is that essentially you expect the output of this code to be like roughly at the same order of its elements, of the individual parts of this vector x, right? But notice that xi squared doesn't fit cleanly into this bound, right? Like, so it could easily leave the range of values, and then what's taking you back is the square root at the end. But it might be that you just get infinity in your code before you can even get to that point. So these are the kinds of things that can happen in numerical code. What can I do to, by the way, when elements of X are really small, then what can happen? Yes? It'll lose precision. You can have a phenomenon called underflow, right? So think about, like, for example, what if all of the elements of X are identically equal to the smallest non-zero value that I can put into IEEE floating point precision, right? Just to be evil. Well, we know that the norm of that vector is going to actually be bigger than that value. But every time I do that square, right, this innocent-looking piece of line of code here, what is the square of the smallest number that's like bigger than 0 in IEEE? Just 0, right? So somehow the accuracy of this piece of code is not so good, even though it looks like the mathematical formula we had. Yeah, that's the sort of theme that I want you to get out. So what can we do to solve these kinds of problems? Well, essentially, you have to look at a piece of code really critically and like look at every single add, subtract, multiply, divide, square root, whatever, and ask yourself, is this going to traverse different scales? And if so, how could I cope with that? So for example, to address this particular problem, I think a very simple thing that one might do would be, compute the maximum element of my entire list of values, and then compute the norm scaled by that maximum value, and then scale back. Why would I do that? Well, now, in some sense, I've taken my list of numbers, and I projected it onto a list of numbers where the biggest value is plus or minus 1. And that's like in a regime where double precision makes sense. And now I can go back and undo that little estimate at the very end. Cool? Yeah.
I take it that like a lot of these considerations have been solved for and like handled
Mm-hmm.
as a person who's like programmed, throughout my life.
Mm-hmm.
I don't think about this ever. And so
Ah.
historically, like, have bugs popped up as people have worked on numerical software, and that's just been a back and forth.
Absolutely. It's a fabulous question, which is like, well, I don't think about this when I call, PyTorch, vector.norm. Well, I'll give you two answers. One is you better, because every once in a while it's going to fail in some weird way. I think a lot of numerical code kind of implicitly assumes that your values are in some range, but they don't tell you that. Actually, PyTorch is a good example because they rewrote a lot of the basic kernel, and some of them is reliable and some not. These days it's probably pretty good. Like 5 years ago, a little less so. And you're absolutely right. There's a push-pull. People run their numerical code. They see something is unpredictable, and then we go back to these basic things. I mean, if you were a morally correct, like if you go to the math department, you take the version of this class, you would spend a few weeks on these kinds of problems, and you would work out actual bounds on the error of every single calculation that you do. You can do this. So for example, like if I know that I get a multiplicative error of 1 plus epsilon on every single time I do an addition, you could ask, like, what is the best way to add up a list of numbers? Right? Totally reasonable question from perspective of error bounds. The formalism of doing that kind of calculation is really, really tough. Requires a lot of really tricky application of inequality and this kind of thing. But there is an entire corner of math that's built around that. Last year we had a homework problem that actually walked you through an example. Maybe for fun we can just post it on the, I didn't include it in the homework because everybody hated us. But we can include it on the Piazza if you guys want. You can see just like what that kind of calculation looks like. But yeah, if you look at like a numerical methods textbook from the 1970s, they'll have chapters of just going through these bounds one calculation at a time. Yeah, I mean.
Question out of curiosity, let's say you normalize by the sum of the absolute values.
Uh-huh.
Is there like a specific benefit of doing that over this, or do you have like
So the question was like, why not take the absolute value, take the L1 norm and use that as opposed to I took the max. I think usually a kind of safe thing, just generically speaking, numerical methods is to get your calculations to be in the range of 1 rather than something that could kind of fluctuate. I'd have to think a little bit about where, so there's, let's see, I always get this wrong. Is it L1 norm is smaller or bigger than L2? Well, I will actually prove this later in this course, but essentially I would worry that this would just add to a different overflow or underflow. I'd have to think about it. We'll come back to that. Okay, but actually, here's actually a subtle thing. So does this piece of numerical code fix all of the bugs that might happen here? Yeah. Not underflow. In particular, here's a really weird phenomenon. Let's isolate an even simpler piece of code. Let's say that I want to write a piece of code for summing up a big list of numbers. Okay? This looks pretty innocent. I think we've all coded some version of this before in our lives. What could go wrong? Well, let's think about my list of values xi. And here's a really weird thing that from like integer universe makes no sense at all, which is that if I reshuffle my list of x's, I could get a completely different piece of output for this code. Yeah? So in particular, let's say that my list of values looks something like this. 10 to the 5th, and then some really small number, and then some really small number again, and then some really small number a bunch more times. And let's say that I have this like 10 to the 8th more times. Okay? So here's the thing. I could be in a number system where adding epsilon to 10 to the 5th just gives me 10 to the 5th again, right? But notice that if I summed this list of values backward, right? Now, I actually, by the time I get to the 10 to the 5th, I actually have a significant value. Now, this is an extreme example, but you can see how this actually can come up in practice, right? This is the kind of thing that's like totally counterintuitive. I think we're used to thinking in algorithms about like the order of our list here not mattering, but in this case, it actually does. Any ideas how I could fix this problem? Yeah. I could sort it, absolutely. In some case, and that's right, I could sort by absolute value. What did I lose? Yeah, right? Like it feels like summing up a list of numbers should take order and time, but if I sort it, then it's n log n. Not the biggest, loss, but wouldn't be so great. So it turns out we're running a little late, so I'll forward you to the textbook for some details. But there's an algorithm that actually is really, really clever out there called K-Han summation, whose job in life is to do exactly this kind of thing. Like, how can I linearly sort up a list in such a fashion that at every step, my numerical error stays in the regime of the last couple digits? And the trick is going to be as follows. It's really sneaky. This is, the idea is something called compensation. The basic idea is that if I take two values, I can add them together, and then I can subtract them again. And notice that I might not get 0, right, because of rounding that happens in every single step here. This value here is called compensation, right? It's sort of like the error. And notice that like in one regime where I go from small numbers to big numbers, when I add, that's where the rounding happens. When I go from big numbers to small numbers, like 10 to the 5th minus 10 to the 5th plus 1, if I were somehow able to represent that in my number system, like that subtraction is actually kind of okay, right? Because I could already resolve it in the digits that I had. And so what does K-Han summation do? Well, it's a really glorified, simple idea. You essentially do the algorithm that was on the previous slide, so you just add numbers on your list, and then you immediately subtract the number you just added and add that difference to a second value, which is going to be your compensation. It's the estimate of the error. Okay, so I'll let you read about that in the textbook. This is just to say, like essentially in this class, we're not going to worry about low-level numerical stuff all that much, because I think that's not the exciting perspective for most of the people in the room that are interested in computer science applications. But it's just to kind of highlight to you how subtle these kinds of problems are, and to get you thinking every time you look at a piece of code, things that look completely reasonable from perspective of mathematical formula are actually pretty unreasonable from numerical one, unless you implement it super carefully. By the way, a really famous example of this that does show up in machine learning is something called softmax. Right? So in particular, what does the softmax look like? I always get this wrong. It's the exponent of the sum of the logs, or the other way around? So the other way around. So it looks like log, because e to the xi, like that. Which thing is like actually a nice differentiable approximation of the max over all the I of xi. But you can see what's going to go wrong, which is this thing can explode. Right? So let's say that I have a list of length 1. Right? And say xi is like 10 to the 8th, right? So e to the xi is probably ginormous, but then I immediately do a log after that, right? So actually most implementation of log sum x, like this softmax, which shows up in all of your machine learning code in case you thought this was irrelevant to your life, does not implement this formula. It implements a clever numerical thing where you kind of like shift by a constant here, and then you guys should, I think you have to add c out there. I think. Is that right? Yeah, that feels right. Okay. So anyway, that's my point. Is essentially all of these things are really subtle. In fact, here's yet another example. If I want to approximate the variance of a list of numbers, this is a formula we all know and love. But of course, if I code it here, you can see that it combines all of these things. You have vector norms, you got summation, all that good stuff. Okay, I think I'm done harping on numerical precision. We should actually talk about some algorithms in this class. Any questions before we flip to a new topic? Fabulous. So we're going to launch the new phase of this course. I'm like way behind where we were last time I taught this, which isn't great, but that's okay. Where we're going to talk about solving linear systems of equation, and in particular, we'll start by deriving the most famous matrix factorization. I think it has the longest history, which is something called LU. By the way, kind of a cute thing that happened in this area of math is that rather than like naming it after some problematic mathematician or something like that, we just name them after the letters that we tend to use for the variables in our formula. I think that's kind of fun. Plus, like, enough things are named after, like, Gauss. Okay, so in any event, our goal in this class is going to be to solve linear systems of equations extremely efficiently and using as many different methods as possible, not just for like fun trivia, but also because what we'll see is the different linear problems actually require very different algorithms. Okay. So in general, in this class, oops, oh no. We're going to be, what is the basic linear system of equation we often want to solve? We're given a matrix A and a right-hand side B, and our goal is to find X. In the most generic case, maybe A for some reason is non-square. And again, because remember that before we talk about algorithms for solving a problem, we should first talk about whether we can solve that problem at all, right? And I think this is the simplest case where the story is probably familiar to you from linear algebra class. Right, like we already know. Like somehow I think in our minds we look at this and we think like, oh, well, if we're going to talk about algorithms for solving linear system of equation, then obviously X should be, or A rather, should be square. That's actually not the case, right? There are plenty of linear systems that look totally weird from perspective of undergrad linear algebra, but you could imagine a piece of numerical code solving. So let's give a few examples of things that are going to be solvable and things that aren't, just to kind of put us all on the same page. Here's a linear system of equations that's very clearly solvable. And we'll call this completely determined, right? Meaning that essentially there's exactly one solution to this system. Anybody brave enough to tell me what it is? Yes. Yeah, so like notice that hopefully we all remember how to do matrix vector multiply like that, right? So this is X equals -1, Y equals 1, yeah? Linear systems tend to be pretty easy when the left-hand side is the identity matrix. But one thing that I think is a little bit subtle that we don't talk about, like when we talk about linear systems being solvable, we typically think of that as a function of the matrix A, but that's not strictly true. So for example, here's a linear system of equations. What is this linear system of equations? It's basically X plus 0y equals -1, and X plus 0y equals +1. Is this thing solvable? No, this is what we would call overdetermined, which makes sense because there's two different values for X here, right? Or what could I do? Well, I could just adjust the right-hand side of this problem to -1, -1, and now I've got infinitely many solutions, right? I can choose any value of y that I want. Now, this feels trivial, but my essential point here is when you talk about solvability of a linear system, it's actually a tiny bit more subtle. It's not just a function of the matrix. It's also a function of the right-hand side. Do you see that? Like, here's a right-hand side where this is not solvable. Here's a right-hand side where it is. Yep. And in fact, you could ask, if you were being kind of a smart-ass mathematician, whether there's some other case we haven't thought of, and the answer is no. So in particular, if I have two distinct solutions to my system, then I actually have infinitely many, right? There's no such thing as a linear system with exactly 3 solutions. In fact, this proof is so easy, we might as well do it. Let's say that I take any real number t, then notice that if a x0 is equal to b and a x1 is equal to b, then one thing that I could do is make a new solution, which is t x0 plus 1 minus t x1, right? Infinitely many of these for all the different values of t. This is, of course, t a x0 plus 1 minus t a x1. These are both equal to b, and these add up to 1, so this is b. Yeah? Okay. Right. So that's my basic point. That like when you can solve a linear system of equations, we talk about solvability and even conditioning. There's a universe where that actually depends on both the matrix and the right-hand side. We're going to see there's shorthand where it only depends on the matrix, but that's not strictly true. And there are cases that show up in practice where you actually want to invert a matrix that, for example, has a 0 eigenvalue. Invert is probably the wrong word in this case, like solve a linear system. So as probably the most famous example in physics, you might want to solve Poisson equation, right? So that's like Laplace of a function equals 0. If you don't know what that means, it's fine. Laplace is like the thing that takes a function and maps it onto its second derivative, right? Notice that like x squared, I guess is one of those, or x, rather, sorry. Well, strictly speaking, this thing has a 0 eigenvalue in the sense if I take a constant and I add it to f, then that's sort of indistinguishable from perspective of this matrix. But physicists still want to solve this problem just like up to a shift, right? So there are cases where you actually do care about these kinds of things. In fact, one thing that we prove in the book, I think I'll skip it today. Last year I proved these things, but really it's just a linear algebra exercise. Is that solvability can depend not only on the right-hand side, but also on just the shape of your matrix. So for example, if I have a tall matrix, does everybody know what this means? So like if I have a matrix A, by the way, our notation here, what we're going to say is R m by n, meaning I have m rows and n columns, right? So tall means that m is bigger than n. Right? Then essentially for any tall matrix, there exists a right-hand side for which it is unsolvable. Similarly, for any wide matrix, there exists a right-hand side with infinitely many solutions. That like kind of falls into this category. If you want to kind of think about how to prove these sorts of things, there are many different ways to think through matrix vector products. The one that I usually think about is as follows. Like, I can sort of draw a schematic. So like if I have A times X, I can think of A as like a bunch of vectors, right? Each of which is just kind of sorted in my matrix one column at a time. All right, then X has got a bunch of values like that. And remember, like, what does matrix vector product do? Like, it goes like this, right? So in some sense, matrix vector product is just shorthand for a linear combination of the columns of A. Right? So from that perspective, now you can derive these two propositions pretty easily, right? Because if you're a tall matrix, right, what does that mean? That means that the dimension of these vectors is bigger than the number of columns, right? Meaning that essentially these columns don't span that space. So the right-hand side you would choose would be outside of that span. And I'll let you think about the wide one, okay? But in any event, all of this is just to say that when we talk about solvability and conditioning and stuff, it's always subtle, even in linear algebra problems that we know and love forever. That like we just have to be so careful with all of our definitions and so on. That said, in today's lecture and for the next couple lectures, we're going to assume that all of our matrices are square and non-singular. For now. We're going to return to this case later. Okay? Notice that this is actually a little bit subtle. So in particular, we just spent a lecture and a half talking about how we can't do any calculation up to 100% precision, right? And so a reasonable question you might ask is like, what does it even mean for a matrix to be invertible? In particular, notice if I look at this matrix here, for any epsilon not equal to 0, this thing has an inverse, yeah? But I can take epsilon to be awfully small, right? So the borderline between invertible and not is really, really shaky. Right? In fact, it's some weird polynomial condition in all of the elements of my matrix, right? And that's going to be a problem because essentially invertibility and conditioning are going to be tangled together in a really messy way. That make sense? Okay. So, in the remainder of today's lecture, we're going to do a thing that I hate. I'm so sorry. Everybody has to do it at least once, which is left over from your undergrad linear algebra class. I'm guessing you've all done it before, which is we're going to solve a linear system by hand. I'm so sorry. It's no fun. Nobody likes to do it. But we're going to do it with the perspective that we're trying to think about how to derive an algorithm so that we can save future grad students from having to do the same calculation. Okay, we want to write a piece of code. One thing that we can do, and here's going to be our example linear system. Luckily, I have engineered this linear system to have an integer solution. I want to be clear, not all linear systems do. So here I have some set of relationships like y minus z is equal to -1, 3x minus y plus z is 4, so on. And my goal here is to solve for x, y, and z. I promise this class gets harder. Like, you guys all are like rolling your eyes, and like 3 weeks from now, you're gonna be complaining. Okay. In any event, we want to write a piece of code that just inputs some system like this, and then outputs the actual solution, like X, Y, and Z. And so far, our main state-of-the-art piece of code for most people in this room is probably to do it by hand, right? Like, it's like this fun party trick that I feel like everybody does in linear algebra class, which is this thing called row reduction, right? So typically, you take a system like this, and you write in this sort of schematic form, like this matrix on the right-hand side. Notice that all I've done is kind of arranged the coefficients in a big square. And then you do these little operations that each correspond to some simplification of your linear system. So we're going to do a step or two of this thing, just because, like, you know, what would be a linear algebra class without a little bit of excruciating pain? And what we're going to see is that they map on to relatively simple algorithmic steps that we can codify pretty easily, right? This like goofy party trick that we do in undergrad linear algebra is completely worthless. I regret to inform you. Okay? And in fact, that's going to be true of a lot of goofy party tricks you do in undergrad math class. Like this like simplex algorithm by hand is another good example that's even more painful. We probably won't get to that in this class. Okay. So in the textbook, I go through the steps of simplifying this both on the form on the left-hand side and the form on the right. Hopefully you guys are okay if I just do it on the right-hand side, and we're going to think about what it means to do on the left. Okay? So essentially, notice that like we start with some form like this, and our goal is going to be to map it onto something where the left-hand side kind of looks like the identity matrix, and the right-hand side is some vector of values, right? Because then it's kind of like x equals something, y equals something, z equals something. Cool? Okay, so let's start with this thing, and we're going to see how many mistakes I can make in the span of 2 minutes. Okay, so our thing, we got 0, 3, 1, 1, minus 1, 1, minus 1, 1, minus 2. We got a minus 1, 4, and a minus 3. Remember, our goal someday is to get to something that looks like identity and some darn thing next to it, and that's going to be the solution of our problem. Yeah? And basically, my point is that for every manipulation you can do on the like equations on the left-hand side, that corresponds to kind of a nice graphical thing we could do to this table on the right. So for example, like at the end of the day, we probably want the upper left element of our matrix to look like a 1, right? Currently it's a 0, and like obviously I can't scale that by anything to get to a 1. So what might I do? Well, one thing that I could do would be to swap the first and the third rows. I'm going to use this ambiguous squiggle here to mean a step of Gaussian elimination. Oh no, I gave it away. So in particular now I have 1, 1, minus 2, minus 3, 3, minus 1, 1, 4, 1, 1, minus 2, minus 3. And now at least one of our elements here agrees with what we wanted. Cool? Did I already make a mistake? Oh, man. I'm terrible at this. I'm sorry. Thank you, by the way, to the people that already found critical math mistakes in the first, like, 6 pages of the textbook. Now we're good? I see a few nods. OK, I'll take it. OK. So for fun, well, here is, like, kind of annoying, right? Like, I would expect the first column to be 1, 0, 0. So maybe our next step is to eliminate that 3. How could I do that? I know you guys know this. Like undergrads, you guys are like programmed from birth to do these things. You're all grad students. Yes. Yeah. So I could take the first row, scale it by 3, and then subtract that from the second row. Yeah. What does that correspond to in our system of equations? Just to make sure that we understand that this is like not just like some abstract thing. It's basically like saying, take one of these relationships and just multiply both the left and right-hand side by 3, right? And then subtract it off from another relationship, right? Like I feel like sometimes we get so used to what is this stupid term, like computing row echelon form, that we kind of forget that it's like just mapping onto like very simple operations. So in particular, I'm watching the clock because this is going to take forever. When I do that, I'm going to get, well, the first and the third row remain the same, right? So I got a 1, 1, minus 2, minus 3. I got a 0, 1, minus 1, minus 1. And what's going to happen in the middle? Well, we designed it to get a 0 there. Conveniently for you guys, I have in my notes what happens to the rest of the columns because I'm bad at arithmetic. I get 1, minus 1, minus 1. And again, that corresponds to take the first row of this matrix, scale it by 3, and subtract it from the second row. Cool? All right. So now, oh, did I already make a mistake? I don't think so. Oh, yeah, I did. Sorry. What was that? Oh, I'm sorry. Wait, what have I done here? Oh, I'm sorry. Every time I do this. The good news is I believe it's in the slide. It's not. Okay. 0, 1. Oh, no. What did I do? All right. Well, my notes are completely wrong. Okay. Yes. Ah. So I just. Yeah. So. Wait. Okay. Well, this is embarrassing. Rather than trying to fix my arithmetic on the fly, what we're going to do is the following. You guys are going to row reduce this matrix at home. And what you're going to see is that when you do that, essentially all of the steps of your algorithm are very simple, right? All you're doing is swapping rows of your matrix. I'm sorry, I had terrible food poisoning last night. I'm just trying to make it to 12:30. And it basically corresponds to 3 operations. One is swapping rows of your matrix, which corresponds to just reordering these formulas, right? One is going to be scaling a row, which is like multiplying the left and right-hand side by the same value. And the third is this weird operation that apparently I can't do by hand. This is why I write code for this stuff, where I take one of the rows, I scale it by a constant, and I add it to another. Okay? All right. I'm sorry, that's horrifying. You guys are all going to drop this class because I'm tired. Okay. So here's the basic cool idea that's going to matter algorithmically, since your instructor is apparently bad at arithmetic, which is as follows. Every single step of solving this linear system of equations, which like I think we usually think of as like this fun shell game where we're like permuting rows and scaling them, can be thought of a different way, where I essentially start with my matrix. I'm going to quietly keep erasing things that I'm not confident in. A, and then going to pre-multiply it by a matrix that carries out each of the steps of the algorithm that we implemented. So for example, if I want to scale the rows, that corresponds to like pre-multiplying by like maybe a diagonal matrix, right? Swapping the rows maybe corresponds to like a permutation matrix. And what we're going to see is that basically this whole technique is built out of 3 different steps. Have I lost you guys? I can try and do this row reduction again. I'm like, totally embarrassed. I'm having a tough week. Okay, so let's see exactly what those matrices are. So first, if we want to permute the rows of a matrix, this is actually a very simple thing to do. So let's say that I have a map sigma, which is reordering the rows of my matrix, right? So it takes indices 1 to m and gives me some new set of indices. Then I can construct a permutation matrix whose rows are basically the standard basis vectors permuted the same way. And that thing is the permutation matrix that carries out that calculation. Okay? Moreover, I think row scaling is probably the easiest one. This is where I pre-multiply by a diagonal set of values, a1 through am. So that only leaves this one last weird operation, right? Where like I take one row, I scale it by a constant, and then I add it back to another row. Right? That's the one last thing that we got to implement in linear algebra. Does that make sense? So let's see if we can do that. I'm like really horrified. I even wrote it all down, and it's just completely wrong in my written notes. I don't know. Huh. Okay. Right. So here's a fun thing that we can do. I think a lot of the linear algebra tricks that we think of as just like weird formulas that we learn once by rote are actually very intuitive, despite my, my bad math here. And let's see if we can kind of code this up in some mathematical sense. So in particular, our goal here, and I'm going to go ahead and have a spoiler alert and put the formula on the slide, but let's see why this is the right thing to do. It's going to be to take row k of a matrix, scale it by a constant c, and then add the result to row L, right? That's our goal. Okay, so here's the question. How can we implement this in math, as it were? Well, the first thing I have to do is isolate row k of a matrix, yeah? So here's kind of a clever trick. So let's say that I have some matrix, you know, whatever elements it's got, and I pre-multiply it by a row vector. Let's say like 0, 1, 0. What's going to end up happening when I pre-multiply it by 0, 1, 0? Yes? The second row. Why is that? Well, remember matrix vector multiply. I go down on the right-hand side and left to right on the left-hand side. Right? And every time I do that, I scale the first row by 0, the second row by 1, the third row by 0. Similarly here. Right? So I end up with just this row of the matrix. Does that make sense? So in general, when I see the expression EK transpose times A, this is equal to the kth row of A. I kind of like thinking about a formula this way because it's sort of like thinking about programming with like math formulas a little bit. Okay, so that was step one. I isolated row k. Now what do I need to do? Well, I got to scale by c, right? So that part is easy. So that's c times ek transpose A, scaled kth row. And now I need to add it to row L, right? So here's one way I could break this up. I could say that this is equal to the sum of my matrix plus another matrix which is 0 everywhere except on its Lth row. And in that Lth row, it should be a copy of this thing, which is a row vector. Hopefully you guys all agree with me there. Does that make sense? Yes?
You're saying Lth row, but you're on the kth row.
Absolutely, I'm probably, no, I got it right this time. You isolate the kth row, and then you want to add it to the Lth row. So essentially what I want, like let's call this vector V. I want a matrix. There's going to be like a bunch of zeros, and then V, probably V transpose because it's a row vector, and then a bunch more zeros, where this is row L, right? And then I'm going to add that back to A, and that's going to be my operation. Does that make sense?
So E sub k transpose A is the kth row, right?
This is the kth row of A, and now I want to move that to row L. Yeah.
So then C is the constant?
Yeah, C is just the scale. Yeah. So how could we implement this in math? Like what's our formula for a matrix which is 0 everywhere except on row L, which is this vector V? I mean, the fact that it has this expression kind of doesn't matter. Yes? Multiplying the other side. Not quite. Yes? Cross product. Let's say we're in R7. Yes? Outer product. There we go. But I'm not sure if you're a language model or you know what that means. So let's write the actual formula because it's quite simple. In particular, this is just C E L E K transpose A. So in general, if this is a row vector, so what is EL? Well, EL is going to look like, you know, a bunch of zeros, a 1, and then more zeros, right? And now I've got a vector V like this, right? I've got to keep thinking about matrix vector products. What is the first? So first of all, if this is going to be like n by 1, and this is going to be 1 by n. So what is the dimension of this product? N by n. And what is this product? Well, think, you know, matrix vector multiply. It's kind of easy this time because there's only one column on the left. Yeah? So the first row is going to be all zeros. Do you see that? Second row is going to be all zeros. Let's say that this is the Lth element. Now, let's just a scaled version of V. Do you see that? So does everybody see what's going on here? So again, this thing is a row vector where I isolated the kth row of A. And now this thing is going to make a matrix that took the kth row of A, puts it in row L, and puts 0 everywhere else. Cool? So finally, we can implement our elimination operation, which is good because I failed to do it by hand. Okay? And what's going to be our expression here? Well, it's going to be basically A plus that, right? Because again, I wanted to start with my original matrix, take the kth row, and add a scale of that to the L. Cool? And of course, we can factor this expression. This is equal to identity plus C E L E K transpose times A. Right? So notice, this object here has no A dependence. Or it does, I mean, like, obviously C is going to depend on A, but like the abstract version of this doesn't. So basically, what have I shown you? Well, I've shown you that the 3 operations we need for a more capable mathematician than your instructor to carry out Gaussian elimination by hand, right? What do they correspond to? Row scaling, which is like multiplying by identity matrix. Permutation, which is like multiplying by a permutation matrix. And this other weird operation, which we'll call elimination, where you take a row, you scale it, and you add it to another row, which takes this form. Okay? So in other words, when we did that elimination by hand, essentially what were we doing? We started with the matrix A, and then every time we did a row operation, we multiplied by a matrix of one of those 2 forms, like that, all the way to E, I don't know, what's the letter we haven't used yet? Q, where Q is the total number of steps that I ran in my technique. Does that make sense? And when I'm done with this, remember that, like, abstractly, I get identity there. So implicitly, what does that mean about this giant matrix vector product? Well, it actually means this product is just equal to the identity, right? Because in some sense, that's exactly what our algorithm is trying to target, yeah? So essentially, that's my point, that if I run row reduction, I do Gaussian elimination by hand, this corresponds to multiplying on the left by a sequence of matrix of one of 3 very simple forms, right? And by the way, what does that mean this matrix product is equal to? A inverse. Now here's going to be kind of a cool thing. What's the inverse of a diagonal matrix? It's also diagonal, right? Just diagonal of 1 over the elements. What's the inverse of a permutation matrix? It's also a permutation, just the transpose. What's the inverse of an elimination matrix? That one's a little trickier. What we're going to see is just flipping the sign of C. Oh, sorry, I guess I covered it up. But like, you know, if I added 3 times the first row to the third row, right? If I then subtracted 3 times the first row to the third row, then like I get back the identity. So basically, here's my point. Each of these matrices has a really simple formula for the inverse, right? So notice if I multiply them all together, I get A inverse, and that's going to be a pretty simple thing to do, right? So implicitly, in our steps of row reducing the matrix by hand, we computed the inverse of A, yeah? And that, in our next lecture, is going to be how we derive matrix factorization and how we solve linear systems. Now, to give a few footnotes before we call it for the day, one kind of numerical rule of thumb is never to compute the inverse of a matrix if you don't have to. That essentially, notice that like even when you did it by hand, you carried around that B there, and that's actually quite important from like a numerical perspective. Why is that? Well, let's say that I have a linear system like the following: 1, 0, 0, epsilon times x, y is equal to, I don't know, whatever, 7, and then just like 0, you know. Computing the inverse of this matrix is quite ill-conditioned because of this epsilon, right? You're dividing by a small number. But actually, this linear system is perfectly well-conditioned because it's pretty clear what you should put in the second element. Yep. This case is pretty obvious, but you can imagine this hiding inside of some more complicated thing. OK. So essentially, what we're going to do at the beginning of our next lecture, I promise I'm not going to make a single mistake, is we're going to go back through our steps of row reduction, right? This idea where you kind of take this augmented matrix and then end up with this system of equations. And we're going to introduce an algorithm called Gaussian elimination, which is basically just coding those steps that we have all done a billion times by hand. Okay? And what we're going to show, the first version of it is going to show how to get the inverse of a matrix. The second is going to give us actually a really nice factorization. Okay? All right, guys. So my apologies again for making a stupid math mistake. That's really embarrassing. That's on me. But the good news is that the textbook does precisely this example, and I'm like 82% sure it's right. So take a look there, and next time we're going to talk about matrix factorization. And take a look at your homework if you haven't. Oh no, I forgot to actually record this class. I set this whole thing up. Oh, shit. I forgot to